Hello, I'm recording this video to show how to simulate a Scour using Flow3D software. We use Flow3D version 11.04 to simulate a Scour in this video. Let's select the software to start. First of all, we need to define new workplace in one of our computer folders. We define it in one of our empty folders because some of Flow3D models has more than 20 gigabytes space. I define it in my computer D folder, for example. Then OK. We need to define a new name for this workplace. After that, our models and our new works will be saved in this new workplace. For defining new model, we need to select file and add a new simulation. I use Scour 1 as a name for this model, and we can see from this address that the model will be placed in our workplace that we defined it. Then we click OK. We continue from model setup. I need to change my computer language because now it is in Persian, and you cannot realize Persian language now. I need to change my computer language. uh, let me to close and restart the program. I wanted to see if the problem has been solved or not. Yeah, you can see the language problem now has been solved, and in this part we need to define a time for our model. For example, we can define 100 seconds for this model. It is important to define SI units, and after that Celsius for temperature, and interface tracking. We need to, because we wanna simulate Scour, free surface or sharp interface. Is right for our model, and flow, because we use water, flow mode is incompressible. If I wanna explain more about finish time, we don't need to wait to finish this time, because the state of each model is important for us. When we start to run a model after depending on each model properties, after a period of time we can check the stability of your model from this section. So if you see these sentences that simulation is nearby to steady, it shows that you can stop your model, and it is no need to continue. So I wanted to say that you don't need to continue the model during whole this 100 seconds. Number of fluids, we have one fluid, and there is no additional thing in this section. After that we need to define the physics of our problem. First, we need we going to define which turbulence model we want to use in the simulation. As you can see, three turbulence model there are in this software: K epsilon, RNG, and K omega, or other turbulence model large eddy simulation. You can use one of these models. Sometimes you wanna extract the results of each model and compare the results together, and finally select the best model. In this model, in this simulation, we use, for example, K epsilon, and then OK. Gravity and non-inertial reference frame. As you know, because gravity is in Z component, we define, because because gravity acceleration is in Z component, we need to define it, and then okay. After that, because our simulation is about Scour, we need to define the sediment properties. In a simple simulation, we define uniform sediment, and if we have different diameters for our sediment, and we have information about the percentage of each diameter, we can define different sediments and define different properties for each sediment for conditions that we have a sediment that has been formed from different diameters and it is non-uniform. In a simple simulation, we start with one sediment diameter. We can name it as a sand 1, and we can introduce its diameter as a 1 millimeter, 1.4 millimeters, and other parameters you can see: critical shells number, entrainment coefficient, bed load coefficient, angle of repose. These coefficients are your tools to validate software from different papers. There is one way to validate software. If you don't get acceptable results, you can work on these coefficients and change them in a better way to find optimum values of these coefficients, and to validate the software with results of some experimental and some other papers, but in the simulation, I don't want to change this software coefficients because we want to simulate an example in the first. So I click on OK. There are different sections in this physics section, and they are for different problems, different issues, like porous media, like heat transfer, like granular flow, like shallow water problems, and other. After that, we need to define our fluid, that is water. We define it in from material section fluid database, and we select the water and load fluid then okay, close. We now can see from this section, fluid section, that fluid is water, and we defined it successfully. After that, when we finished physics and fluids, we need to define geometry of our problem. In this example, we wanna simulate a score after a score to jet outlet from a gate. There are different ways to draw your geometry. For example, you can draw it from these tools that you can see, but one of simple tools that is you input your geometry as a steel file that you have drawn it in AutoCAD or something, some other softwares. For this example, I made the geometry in AutoCAD, and I extracted STL files from AutoCAD. I wanna use those STLs in this example. First, I input gate as a STL file. I saved it in my desktop, and yeah, okay. Gate, it is a solid object. Yeah. Let me to input sediment as a steel file, it is different from our first steel because it was in the form of a solid, but sediment is different. Yeah, okay. In this section we need to define it as a packed sediment, and it is not solid. We name it sand. Okay. We now can see the geometry through this opening space equal 2 centimeters under this gate, that the flow will act as a jet, and the score will be happened in our sediment pack. I use another solid object after this sediment pack because it will keep our sediment stay between this our experimental area. You can see now. Now we need to define our mesh using mesh window, add mesh block 1. First we define our mesh using this option fit to geometry, and we use cell size, for example 1 centimeter as our mesh cell size. You can see that mesh fits to our model, but in this example we define half a meter before the or 30 centimeters before the gate to define our boundary conditions, and after our sediments we define another space to show our another boundary conditions. We don't need to have 1 meter in Z section, and you can see define it, for example 18 centimeters. Now we have different mesh view options. You can see another mesh view option, but it is simple, and we can see our model. Now it is time to define our boundary conditions. From this option you can see the number of cells. Yeah, you can see from this section the number of cells that you have produced. From this part we will define our minimum X boundary condition. For example, we can use volume flow rate or specific pressure or something like that. Mostly we use these two sections as X minimum X boundary condition. The elevation of our gate opening is 15 centimeters, so we wanna introduce 60 centimeter water behind this gate. So we put we define it as a use fluid elevation and 75 centimeter, and then put OK. Now we define 75 centimeters waterhead behind this gate, and for maximum boundary condition we use specific pressure, and we define it fluid elevation. For example, I said that the elevation of our sediment is 15, so we can define our maximum X boundary condition or water level in the end of our model. For example, 30 centimeters, like 15 centimeters. We have 15 centimeters water above our sediments. Y minimum we define it as a wall. Maximum Y we define it as a wall, and Z mean we define it as a wall, and the max because it is in touch with the air. We leave it as a symmetry. Okay, so we defined our boundary conditions, specific pressure, wall, and symmetry. Then click and close this. Now from this section we define initial condition. First we define pressure as hydrostatic pressure, and after that we need to define flood region, because when we define flood region, the model doesn't need more time to simulate our boundary conditions, and the model will be finished in a short time. As we discussed about it, we introduced 75 centimeters water behind this kit. So with limiters, we use we use 1 meter except low, except high, because the location of our gate is in 1 meter from 0, and the water level was in 75 centimeters. We use the high. And another flood region for downstream of gate, we discussed that we have, for example, 30 centimeters water above our sediment, the high. This initial condition help our model to finish as soon as possible, because Our model doesn't need time to analyze all these things. Yeah, and I think that there is no additional thing in this machine and geometry section. From this favor we can see the performance of our mesh cell size. For example, we use render, yeah, and the final model we can see if we use smaller cell size, we can get better and acceptable results. Yeah, but because it is example for beginners, I used 1 centimeter. After that, restart data interval. We define it to show our results during simulation. It is not need to stay to finish the simulation and after that check the results. We can see the results during simulation, and we define 2 seconds to check our results. From this section you can select the type of output you wanna. For example, we hydraulic data, we use hydraulic data, and from section we use hydraulic data. You can use different options: total hydraulic head, strain rate, flood vorticity, flat tracer, or something like that. But for the first it is enough. Yeah. After that, numerics is after. We can use numerics for other settings that I don't wanna change default values in this example. Analyze and display is after finishing our model. So we come back and run simulation. Yes. Yeah, we see one error from this triangular section that usually it shows warnings and also it shows the time that your model is nearby to study. We can see and read this section to solve the problem. Density of sediment spices. We forgot to introduce the density. We come back to define it from sediment scour section. For example, we define 2650 kilogram on cubic meter, for example. then save it and run simulation. Yeah. Also you can see this error that it shows that our mesh size is sediment size is more than 10% of our mesh cell size, but it is important error for our results, but the model continue to simulate with this error, and this error will not stop our simulation. We can check errors during simulation from this section, but the speed of simulation depends on your computer properties and your computer power too. My laptop is weak and is not strong, so simulation takes much time in my laptop, but it is an example, and I don't want to completely simulate a model